In this video, we will introduce randomized algorithms via three basic problems: 3-SAT, sorting, and selection. We will analyze each algorithm and focus on the expected performance. Let's start with the 3-SAT problem. The input consists of n variables and m clauses, where each clause is the disjunction of three literals. A literal is a variable or its negation. The input Boolean formula is the conjunction of the m clauses. For example, this is a 3 SAT formula with 2 clauses and 3 variables. Our goal is to find a satisfying assignment. This is an NP complete problem, and there is no polynomial time algorithm to solve it unless P is equal to NP. But this does not prevent us from trying to approximate the problem. The goal is now to find an assignment that satisfies as many clauses as possible. Here is a simple randomized approximation algorithm for SAT. Given a formula, for each variable xi, flip a fair coin and assign xi to be true or false accordingly. We will show that, on average, this random assignment satisfies at least 7/8 m clauses out of m total. Consider a single clause. Of all 8 ways to assign the 3 variables, there is only one way that does not satisfy the clause. The clause is satisfied unless all 3 literals are false. Hence, each clause is satisfied with probability 7/8. For each clause Ci, let yi be the random variable indicating whether or not Ci is satisfied. Yi is set to 1 if Ci is satisfied, and 0 if Ci is not satisfied. Then the sum of the yi's is the number of clauses satisfied, and we are interested in the expected value of this sum. We know the expected value of yi is equal to 7/8 for each I. By linearity of expectation, the expected value of the sum of the yi's equals the sum of the expected value of each yi, which is 7/8 m. The next problem we'll discuss is sorting. The goal is to take an unordered list of n numbers and return them as a list in sorted order. You probably know that the merge sort algorithm runs in O(n log n) time, and that there is an omega n log n time lower bound for any sorting algorithm in the comparison model. Here we will study a randomized algorithm that is remarkably simple, called quicksort, that is often the preferred one in practice. The idea is very simple. Select an element uniformly at random out of the list to serve as a pivot. Divide the elements into those smaller and larger than the pivot, and recurse on both halves. The worst case runtime of quicksort is O(n squared). This happens when the pivot chosen is always the smallest or largest element in the array, leading to highly unbalanced partitions. We will show that, given a list of n numbers, quicksort returns numbers in a sorted list in O(n log n expected time. For each ij between 1 and n with I less than j, let xij be equal to 1 if the rank I element, that is, the ith smallest element, is compared to the rank j element, and 0 otherwise. Then the sum of xij represents the total number of comparisons made by the algorithm, hence the running time up to a constant factor. We are interested in the expected value of this sum. Consider xij with I and j fixed. Observe that the rank I and rank j numbers are compared to each other if and only if either is selected as the pivot before any element of rank greater than I and less than j. If any element of rank greater than I and less than j is selected as the pivot before the rank I and rank j numbers, then the rank I and rank j elements will be separated into different subarrays by that pivot and will never be compared. Since the pivots are selected uniformly at random, and there are j minus I plus 1 elements with rank at least I and at most j, this occurs with probability 2 over j minus I plus 1. Hence, the expected value of xij is equal to 2 over j minus I plus 1. The sum of xij is equal to the double summation, where I ranges from 1 to n minus 1 in the outer sum, and j ranges from I plus 1 to n in the inner sum. By linearity of expectation, the expected value of the sum of xij is equal to the sum of the expected value of xij. Let k be equal to j minus I plus 1. Since j is greater than or equal to I plus 1 and less than or equal to n, j minus I is greater than or equal to 1 and less than or equal to n minus I. Hence, j minus I plus 1 is greater than or equal to 2 and less than or equal to n minus I plus 1. This allows us to rewrite the inner summation as the sum from k equals 2 to n minus I plus 1 of 2 over k, and we can pull out the constant 2. Now, since the function 1 over x is a strictly decreasing function, the right Riemann sum underestimates the integral. In this example, the area of the rectangles is equal to the sum from k equals 2 to 6 of 1 over k. This quantity is bounded above by the integral from 1 to 6 of 1 over x dx. Therefore, the sum from k equals 2 to n minus I plus 1 is less than or equal to the integral from 1 to n minus I plus 1 of 1 over x dx, which is equal to the natural log of n minus I plus 1. This sum is less than or equal to n minus 1 times the natural log of n, which is O(n) log n. Lastly, quicksort runs in O(n) log n time with high probability. Specifically, we can show that the probability of error, or the probability of the runtime exceeding O(n) log n, is at most 1 over n squared. The last problem we'll discuss is selection. The input, similar to sorting, includes an unordered list of n numbers. Given an index k between 1 and n, the goal is to find the kth smallest element in the list. The obvious solution is to sort the list, which takes O(n) log n time. But we can do better. We can use an algorithm similar to quicksort called quickselect. Pick a pivot uniformly at random and compute its rank L. Depending on whether k equals L, k is less than L, or k is greater than L, either return the pivot, recurse on the subset of elements less than the pivot, or recurse on the subset greater than the pivot. Quickselect returns the rank k element in O(n) time in expectation and with high probability. We can analyze quickselect similarly to quicksort based on the sum of indicators xij. We reduce to a separate analysis for each of the following 4 classes of pairs. For each case, we can show that the expected sum is O(n).